Good afternoon everyone. Today we will discuss about the subject microcontroller and embedded systems. In this we will discuss about the topic interfacing of microcontroller 8051. Under this topic we will discuss about the introduction of the interfacing, then interfacing of LCD with 8051. After that, interfacing the keyboard to 8051 microcontroller and then interfacing 7 segment displays. After that, interfacing of A to D converter ADC with 8051 and then interfacing of D to A digital to analog converter with 8051. At the end, interfacing of the sensor, that is temperature sensor, with 8051. Introduction to interfacing. Microcontrollers are used as the brain to control a large variety of products. In order to control devices, it is necessary to interface, that is to connect them to the microcontroller. For input interface, we use keyboard, limit switch, ADC, etc. can be used. For output interface, we use 7 segment display, LCD display, digital to analog converter, relays, transistor drivers, etc. can be used. Now we will discuss interfacing of LCD with 8051. First of all, we will cover LCD advantages. In recent years, the LCD is finding widespread use, replacing LEDs. This is done due to the following reasons. First of all, the declining prices of LCD. Then the ability to display numbers, characters and graphics. In LCDs, we can easily display any graphic, any character, but in LED displays, we can display only limited characters. Next, it is easy to program various characters and graphics. LCD display, liquid crystal display is cheap and easy way to display text. LCD displays are available in various configurations. It has integrated controller. The LCD display has 2 registers, one is command register, other is data register. Command register is used to command the LCD and data register is used to display the data. By the RS, that is register select, you can select any register. If RS is 0, then command register is selected. If RS is 1, then data register is selected. Data lines DB0 to DB7. Data bus is used to transfer data and commands. To display any character on LCD, microcontroller has to send its ASCII value to the data bus of LCD. For example, to display AB, microcontroller has to send 2 hex bytes, that is 41H and 42H, that is H means hexadecimal respectively. Now we will discuss about the LCD pin description. LCD has 40 pins. First of all, we have pin VSS, that is grounded. Then second pin, that is VCC, here we give positive 5 volt power supply. Third pin, that is VE, it is used to control the contrast. It is used to control the contrast and it is connected to the variable power supply. Then we have fourth pin, that is RS, register select. It is input pin. When RS is 0, then we select command register. When RS is 1, then data register is selected. After that, fifth pin is read write pin. It is also input pin. When read write pin is 0, then data is write. It is used for write, and when read write is 1, it is used for read. After that, we have sixth pin, that is that is enable pin. It is also input output pin. It is used to enable. When data is supplied to data pins, a high to low pulse must be applied to this pin in order to latch in data present at the data pins. Minimum it should be 450 nanoseconds wide. After that, we have 8 data bus pins, that is DB0 to DB7. These all are 8 pins are input and output, that means these are bidirectional data bus. After that, we have LCD command codes. There are also instruction command codes that can be sent to LCD to clear display or force the cursor to home position or blink the cursor. LCD command codes, these are in hexadecimal number system, and in hexadecimal 1 is used to clear the display screen, 2 is used to return home, 4 is used to decrement cursor and shift cursor to left, 6 is used to increment cursor and shift cursor to the right. After that, number 5 is used to shift display right, number 7 is used to shift display left, number 8 is used display off, cursor off. When number A is used, character A is used, display off, then cursor off. After that, C is used for display on, cursor off, E is used, display on, cursor blinking, F display on, cursor blinking, 10 shift cursor position to left, 14 shift cursor position to right, 18 shift the entire display to left, 1C shift the entire display to right, 80 force cursor to beginning of first line, C0 force cursor to beginning of second line, 38 2 lines and 5:7 matrix is selected. Here is the diagram for interfacing LCD with 8051. In this, we have used 8051's two ports, port 1 and port 2. Port 1 is connected with the data bus of the LCD. Register select pin is connected to port 2.0 pin, read write is connected to P2.1 and enable is connected to P2.2. After that, VCC is given positive 5 volt, VEE it is used to control the contrast and it is connected to the variable power supply, VSS is grounded. Sending commands and data to LCDs with a time delay. To send any of the commands to LCD, make pin RS equals to 0. For data, make RS equals to 1. Then send a high to low pulse to enable pin to enable internal latch of LCD. Now we will discuss the LCD program for interfacing. First of all, we give assembler directives, that is cause a time delay before sending next data or command. Pin, that is port 1 pins P1.0 to pin 1.7 are connected to LCD data pins D0 to D7. Pin P2.0 is connected to RS pin of LCD, that is register select. Pin 2.1 is connected to read-write pin of LCD. Pin 2.2 is connected to enable pin of LCD. Now, origin, ORG means origin 0H. It means our program starts from 00H. Then move 38 to accumulator. It means initialize LCD 2 lines into 5:7 matrix. Then we call command write subroutine. A call, absolute call for command write, call command write subroutine. Then a call, absolute call for delay, give LCD some time. This delay gives LCD some time. Then move 0E to accumulator means display on, cursor on. Then we again call command write subroutine, call command write subroutine, then absolute call for delay. This will give LCD some time. After that, move 01H to accumulator means clear display. Then absolute call for command write. After that, absolute call for the delay. Next, move 06 to accumulator means shift cursor right. Then we absolutely a call for command write, call command subroutine. After that, absolute call for the delay, that is give time to LCD. After that, move 84 in hexadecimal to accumulator. It means cursor at line 1 position 4. Then absolute call for the command write, then absolute call for the delay. After that, which character is to be displayed, that is given to accumulator. Here we have chosen G. G is sent to accumulator, move to accumulator, display G letter. Then we call data write. Here we call data write as G is data. Call display subroutine. After that, absolute call for the delay, give time to LCD. After that, move character P to the accumulator. It means P is displayed. Then we call data write subroutine and then call the delay. After that, character C will be displayed and we call absolute call for the data write, then absolute call for the delay. After that, we move character G. It means we have displayed GPCG. After that, we have this again is here label short jump again means stay here. Then move A to port P1, send command to LCD. Here we have command write subroutine. Then we clear pin P2.0 means RS is connected to pin P2.0. RS is 0 means here command register is selected. After that, we clear P2.1. Pin 2.1 is connected to LCD's read write. It means we have made read write pin 0. It means we can write something. After that, set bit P2.2 means P2.2 is connected to enable pin. It means enable pin is made high. After that, we call delay, give time to LCD, because enable pulse has to be high for 450 nanoseconds. For that, we call this delay subroutine. After that, we clear P2.2, then E is 0, then return. Now we have data write subroutine. In this we have A is sent to port 1, accumulator is moved to port 1. After that we set bit P 2.0 means register select pin is 1 means your data register is selected now. Then we clear P 2.1 means read write pin is 0 for write. After that we clear P 2.1 and we set bit P 2.2 that is equal to 1 means enable pin becomes 1. After that enable is made 0 and a delay is called so that a high to low pulse is given to enable pin. Here we have delay subroutine. Here we move R3 with 50 is moved to R3, then 255 is moved to R4, label here 2 is given, then we have label here 1, decrement, jump, no 0, decrement, jump, no 0, then if to R4, if here 1, then decrement, jump no 0, R3, here 2, then return and end. Now interfacing the keyboard to 8051 microcontroller. Interfacing the keyboard to 8051 microcontroller, the keyboard here we are interfacing is a matrix keyboard. The rows and columns are connected to the microcontroller through ports of the microcontroller 8051. Here we use 2 ports of 8051. We normally use 8:8 matrix keyboard. So, only 2 ports of 8051 can be easily connected to rows and columns of the keyboard. When a key is pressed, a row and a column make a contact. Otherwise, there is no connection between rows and columns. This is the matrix keyboard. Here we have used 4:4 matrix keyboard. Here port 1 is the output port and rows are connected to the output port. Rows are grounded with the help of a program. And our columns, that is D0, D1, D2, D3, they all are connected to VCC. Whenever any key is pressed, then there is a contact between the row and a column. Otherwise, when there is no key is pressed, then all these columns, that is input port of the 8051, gives all ones to 8051. Now flow chart for keyboard interfacing. Here we first of all start, then ground all rows. After that we read all columns. Then any key down. If no, there is no key is down, then go back and read all columns again. If yes, any key is down, then wait for debounce. Then read all columns again. Any key down? If yes, then go forward, otherwise go back and read all columns again. If any key is down, then ground next row. First of all we ground first row, then second, third, and we check for columns. If any key is down, ground next row, read all columns, key press in the row. If no, then go back, ground next row, read all columns, key press in the row. If yes, then find which key is pressed. Get scan code from the lookup table that is stored in your program, then return. Scanning and identifying the key. Here we have used 4:4 matrix keyboard connected to the 2 ports the rows are connected to an output port and the columns are connected to an input port. If no key has been pressed, reading the input port will yield ones for all columns since they are all connected to high VCC. If all the rows are grounded and a key is pressed, one of the column will have 0 since the key pressed provide the path to ground. It is the function of microcontroller to scan the keyboard continuously to detect and identify the key pressed. Grounding rows and reading the columns. To detect the key pressed, first of all, to detect the key pressed, the microcontroller grounds all rows by providing 0 to the output latch. Then it reads the columns. If the data read from the column, that is D0 to D3 is all ones, no key has been pressed and the process continues until a key press is detected. However, if one of the column bit has 0, this means that key press occurred. For example, if D3 to D0 becomes 1101, this means that key in the column D1 has been pressed. After a key press is detected, the microcontroller will go through the process of identifying the key starting with the top row. The microcontroller grounds it by providing a low to the row D0. Only then it reads the column. After that, we will ground the row D1 and so on. If the data reads is all ones, no keys in that row is activated and the process is moved to next row. It grounds the next row, reads the columns and checks for any 0. This process continues until the row is identified. After identification of the row in which the key has been pressed, the next task is to find out which column the pressed key belongs to. Upon finding the 0, it pulls out the ASCII code, American Standard Code for Information Interchange, for that key from the lookup table. Now we will discuss the interfacing of 7-segment displays. LED displays are power hungry, that is they uses 10 milliampere per LED. Pin hungry, 8 pins per 7-segment display. Each 7-segment display requires 8 pins, but they are cheaper than LCD display. So, LED 7-segment displays are very commonly used numeric display. LED displays are preferred when there is no constraint of power consumption. A 7-segment display contains 7 segments arranged as an 8 with one common lead and 7 individual leads for each segment. These 7-segment displays can be of two types, that is common anode type and common cathode type. If all the 7 LEDs have common anode, then it is called common anode 7-segment display. By turning on these 7 segments in various combinations, numbers from 0 to 9 and some alphabets like A, B, C, D, E, F, etc. can be displayed. Here we have 7 segment display that is in common anode form. Here anodes of all the LEDs are done common. After that these 7 segments, that is A, B, C, D up to G, A, B, C, these are arranged in form of 8, and 8th LED that can also be used for decimal point. Normally a 7 segment display also has one more segment for display of a period, that is full stop, which is labeled H. If segment A, B, C, D, E, F and G of display are directly connected to port pin Px.0 to Px.6 respectively, then to display an hexadecimal digit, hex codes can be used from the table. For these are the display numbers. To display 0 for common anode, C0 is used. For common cathode, 3F is used. To display these numbers from 0 to 7, these are the codes in hexadecimal for common anode type and these for common cathode type. Now for to display 8, 9, A, B, C, D, E, F, these are the codes for common anode type and these for common cathode type. If more than one display is to be used, then they are time multiplexed, taking the advantage of persistence of vision. The human eye can detect the blinking if each display is turned on every 10 millisecond. The 10 millisecond is divided by the number of displays used to find the interval between updating each display, that is so that display appears continuous. Common anode display are most suitable for interfacing with 8051 since 8051 port pins can sink current better than sourcing it. Here we have the connections for interfacing common anode display to 8051. Common anode terminal of the 7 segment display is connected to the positive 5 volt DCC for positive 5 volt VCC, and here 330 ohm resistance is used. It is current limiting resistor, and segments 8, B, C, D, E, F, G, these 7 segments, and 8th segment decimal point is connected to the port 1 directly. Here this is the connection for only single display, that is when we use only one 7 segment display unit. In this figure, interfacing of 4 7 segment displays, here these are the 4 7 segment displays which are used. In this 2 ports are used. One port is used to enable the display. Here all the displays are not simultaneously switched on or enabled. They are enabled by time. Here we use time division multiplexing, and here one port of 8051 is used to send the data, and this port is connected to all the displays. Port P1 of 8051 is used to provide the display code for all the displays, and port P2 is used to select a particular display in time multiplexing mode. Here this port, suppose it is port 2, is used to on the various displays. First of all, we will on this by using these transistors. Transistors are used to provide the necessary current for display. Here these resistors are used to control the brightness